All right, welcome back, guys. So just to give you a little information, I have somebody in my household has had COVID, so I will be doing everything from home for the next week. So if things look a little janky, it's because I'm just using whatever I have here. So I have, so we're just going to walk through this nature of energy, these notes here. Okay. I uploaded both the sort of like original blank copy, and then I also uploaded a copy with all my additional notes. Like I uploaded a copy of this as well. Okay. So this chapter is thermodynamics, which is basically essentially all about energy and heat and chemical reactions. You can see here, I'm gonna try to zoom this in a little bit. I know it's kind of hard on this. Thermodynamics is the study of energy and its transformations. Thermochemistry is the study of the relationships between chemical reactions and energy changes involving heat. So this chapter really is going to get into where we needed, for the chemical reactions, where we needed to put the state of matter information, because what the state of matter is changes the amount of energy. So for example, if you have, say you have 50 grams of water, well, 50 grams of water is going to actually have a different energy amount than 50 grams, than that same 50 grams of water frozen as ice. So they literally contain different amounts of energy. So the state of matter actually is going to influence the amount of energy that a reaction either has coming into it or going out of it, so on and so forth. Okay. So I put exothermic and endothermic here. The reactions, remember, exothermic is like heat or energy leaving, exiting. Endothermic is entering, coming in. Okay. They give you some definitions here. You can read energy, work, heat. They give you work, an equation for work here, force times distance. It's the same equation. I just wrote it out so you knew what the variable stood for. Then down here, they give you force is any kind of push or pull exerted on an object. I gave you an equation. Sorry, trying to get this here so you can see everything. I give you an equation for force. Force is mass times gravity. Okay. Gravity is a constant. It's 9.8 meters per second squared. They're going to expect you to know that in some of the problems you work on. So I put it in there, highlight it, whatever, make sure you remember where to get that from or what that is. So the next part, they break energy down into two parts. You probably heard before: kinetic energy, potential energy. Kinetic energy, essentially simplified, refers to anything that is moving, energy of motion. The kinetic energy equation, so they have E sub K, energy kinetic, equals 1/2 mass times velocity squared. So be careful with your variables here, because we've got volume in some. Volume will be a capital V usually. This will be like the script lowercase v is the velocity. So kinetic energy is 1/2 times the mass times velocity squared. Okay. And then potential energy is energy an object possesses by virtue of its position or composition. Composition is like what it's made up of. So, excuse me. For example, composition would be, food. Food has energy locked in the bonds because of what it's made up of. You release that energy by breaking those bonds, but it's energy that is stored due to the composition of the substance. Position would be like, having a, if you put a book on a table, it has a certain amount of potential energy because of gravity. If you put a book high up on a shelf, it has more because of its position relative to the ground and the pull of gravity. Okay, so potential energy, here's another equation that they're kind of sort of expect you to know. The potential energy equation of energy potential, E sub P, is mgh, mass times gravity times the height above ground. Okay. All right. Then they give you they give you a potential energy equation of electrostatic energy. To be honest, I don't really do anything with this. We don't do a lot on electrochemistry in our class. If you do electrochemistry type stuff, you would definitely start using things like this, but we don't really focus on it. So I kind of just show it to you guys so you know what it is and then move on. E sub EL is energy, electrical energy. And then they've got like the K is a constant. This is the constant, 8.99 times 10 to the 9th joules times meters over Coulomb squared is the label. This part's the label. Q1 and Q2 are electrical charges for two objects because you're finding energy between two charged particles, okay? And then D is simply distance in meters between them. So that's the equation you can use to calculate that, okay? So the potential energy can be converted into kinetic energy. An example is a ball of clay dropped off a building. You get potential energy when it's at the top of the building. And then as it falls, it turns from potential. It's converting from potential into kinetic. So like, let me get a sheet of paper here. Sorry. Okay. So the one way, the kind of concept of this is they talk about a ball, dropped off a building. Okay. So when the ball is sitting up here, 100% of its energy is potential. And it has no kinetic energy because it's not moving. Okay. As the ball falls, okay, it's converting energy as the ball falls, it's converting potential energy into kinetic. So like if you're halfway down, you would be 50% of the energy is now potential. I'm just doing it as percentages, not actual amounts here, but you get the idea. 50% of the energy would then be kinetic. Okay, now, this is just a really simplified concept of it. Like, it's not like 100% technically correct. Some of you probably already know that some of the energy is lost to other things like wind resistance, friction with the air, stuff like that. But generically, this is the very, very simplified idea. When it strikes the ground, the moment right before it strikes the ground, or right as it strikes the ground, it would be at 0% potential energy from the height and the gravity, and 100% kinetic. All of that, because it has no height above the ground, all of it would have turned into kinetic. Okay. All right. So, okay, so that's this part here. Sorry, the potential energy being converted to kinetic. Okay, units of energy. The SI unit of energy, the most commonly used one is a joule. J, capital J for the symbol. So all they're doing here, this is they're taking the kinetic energy equation that I showed you up here, and they are showing you the labels for each part that you plug in. In other words, for the kinetic energy, you would have labels in joules. Okay, for your mass, you would want to be using kilograms. Okay, for your velocity, you would want to be using meters per second, which then would be squared from the square there. That's why they've already got it squared in here. That's why I just wrote it here, just to show you that velocity would be meters per second, and then you'd be squaring it from this part of the equation. Okay, so these are just the units. So when you're doing a kinetic energy equation, you want to make sure your mass is in kilograms and your velocity is in meters per second. Okay, or if you're looking for either of those, mass or velocity, you want to make sure your energy is in joules. Okay. All right. Another traditional energy unit is the calorie. Calorie is a unit of energy. So like when you read labels for food and stuff, and they talk about calories, that's actually literally the amount of energy that's, according to the manufacturer and packaging, that's the amount of energy that food contains, per serving, total, whatever. Now, 1 calorie equals 4.184 joules exactly. It's a conversion. Okay. Here I put a definition of calorie because that actually will help us in doing some of the problems. 1 calorie is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. So we can use this equation to calculate any one part of this. You have the energy in calories, the number of calories, equals the mass in grams times the change in temperature, the change in temp in degrees Celsius. Okay. All right. Now, if you go back over here, this is something that is kind of annoying. I can't remember if we talked about it in Chem 1 or not, but if you had me for Chem 1 last year, we didn't because this was supposed to be at the end of the year. If you had me for Chem 1 a couple years ago, we probably did. But the 1 calorie equals 4.184 joules. This is a little c calorie, lowercase c. They also have what you see actually on the packaging as a calorie, a capital C calorie, which 1 capital C calorie equals 1,000 little lowercase c calories, or 1 kilocalorie. 1 capital C calorie is a kilocalorie, lowercase c. So just know, like, you really got to pay attention to the capital C or the lowercase c when on your units for these, because they actually mean 2 different things. I don't know why they did it like that. It's annoying, but that's what it is. Okay, moving on. System and surroundings. A system is part of the universe we are interested in studying. The surroundings are the rest of the universe, everything else. For example, if we are interested in the interaction between hydrogen and oxygen in a cylinder, then the hydrogen and the oxygen in the cylinder form the system, and everything else around it would be the surroundings. Okay, so how does this work? Well, we use this idea of system and surroundings in energy transfer between work and heat. So they've actually redone the definitions again down here: force, work, heat, and energy. Okay. So I added some, okay, now to find, okay, over here, sorry, I should have said this with the equation up here. If you ever have to calculate delta T, change in temp, to find the change in anything, you take the final number, subtract what it started as. So final minus initial. That'll give you change in. Okay. All right. So this part they don't have in here, but you need to know this to do some of the problems. There are basically 3 ways you can look at a system. A system can be an open system, a closed system, or an isolated system. In an open system, both energy and mass can be exchanged. Okay, so an open system would be like an open can of pop. You open the can of pop, you've got it open, you could pour mass out. Mass can be changed, it can go in and out, air can go in and out, and energy can go in and out of it. Okay, it can get warmer or colder or whatever. A closed system is a system that can exchange energy but not mass. So that'd be like a closed can of pop. Okay, you in a closed can of pop, you can't lose, or like you don't lose any of the pop or anything, and air can't enter or exit it. The mass that's in there stays. You can't exchange mass, but you can exchange energy. You can make the ingredients in the can colder or warmer. You can cause it to gain or lose energy. That would be a closed system. Energy can still be exchanged. Then the third case, an isolated system, is something that is typically not found in everyday life. And that's a system where it's closed off and you cannot exchange energy or mass. Neither. And I don't even know if your book gives you an example of an isolated system or not. Let me see if I can find it really quickly here. Oh, so the example they give is like an insulated thermos containing hot coffee. It's not really an isolated system, a perfect isolated system, but it in general, the insulated thermos like doesn't allow. That's why it stays warm. Is it doesn't allow heat or matter to enter or leave. Obviously, it's not a perfect isolated system, because if you leave it there long enough, it'll cool off and whatever. But that's the kind of idea for an isolated system. Okay. Alrighty, that's it for this. The homework is going to be posted. If you guys have questions, need help with any of it, please let me know.